Hello, today we're looking at electric circuits, and that's for the paper 1 GCSE AQA Physics paper. So we'll start with static electricity. Now we get static electricity when you get a build-up of charge. Now the word charge refers to the idea of a build-up of electrons. Electrons have charge, so we get a build-up of electrons or a build-up of charge. In this topic, we only ever really refer about electrons because they're the ones in the atom that are around the outside. They're the ones that can move. The protons and the neutrons are static in the middle. They're trapped. As a reminder, protons have a charge of +1, neutrons are neutral with a charge of 0, and electrons, the ones we're most interested in, have a negative charge of -1. Whilst we might talk about electrons moving, we need to keep using the word transfer or transfer of electrons. So we get static electricity when there's friction between two insulators. Electrons will transfer from one of the insulators to the other. So when there's electrons that get added, that means they have a negative charge, or when electrons get lost or taken away, we say there's then a positive charge. So when we have one thing that's positive, one thing that's negative, that's when they'll attract because opposites attract. And when we have, say, two positive things or two negative things, that's when you're going to get repulsion. A big part of this topic is knowing the different symbols that are involved with electricity. So we've got a cell here. The longer line is the positive one. It takes more pen to write positive, and the shorter one is the negative. We've got an open switch just here and a closed switch. That line would be just flat and it would look like a wire. This is a bulb or a filament lamp. A diode only allows electricity to flow in one direction, and in this case it's left to right, the direction of the arrow. An LED is a light emitting diode, so the arrows are moving away, so the light is being emitted. Here we have an ammeter that measures the current, and that goes in series. A voltmeter measures the potential difference, and that goes in parallel. A resistor that prevents current from flowing as easily, it resists the electrons moving. A variable resistor with the arrow through that allows us to change the resistance. This one is fixed, it doesn't change. Here we have a fuse that you find inside a plug, and it's the wire in the middle that will melt or blow if the current gets too high. And here is a heater, something that will warm up. With those in mind, let's start exploring the idea more about electric circuits, and let's start with current. So we'd say current moves from the positive terminal to the negative terminal of a battery or a cell. So in this case, it goes anti-clockwise. And because we're talking about positive to negative, we call that a conventional current. However, we know that electrons have a negative charge. So what happens really is the electrons will move away from the negative terminal towards the positive terminal. So it's opposite to what we normally refer to as conventional current. So whilst conventional current goes anti-clockwise, electron flow, or the movement of electrons, really goes the opposite direction, so clockwise. But we do tend to use conventional current in most scenarios. When we have a current, we have movement, just like a current of water. The water particles are moving. In this case, a current in electricity terms means we just have electrons that are moving, because each electron has a charge. And as a reminder, that charge is -1. The equation that links with that is charge equals current times time, where charge is measured in coulombs, current in amperes or just amps, and time is measured in seconds. And you may see this equation written Q for charge equals I times T, where I is current and T is time. So we measure current using an ammeter, and that goes in series in the circuit. It goes in the same loop as the component that you're measuring the current that's flowing through it. Potential difference, that's the push. So if you didn't have a potential difference, you wouldn't be able to push the electrons around, so therefore you wouldn't be able to have a current. So always see the potential difference as the amount of push that's going on in the circuit. The higher the potential difference, the bigger the push on the electrons. And you measure the potential difference using a voltmeter, and that goes in parallel. That goes across the component that you're measuring, so you create an extra loop. In this topic, there's two equations for potential difference. Let's explore them. The first one is energy transferred, so how much energy you've used up from the battery equals the potential difference times the charge. As ever, energy is measured in joules, potential difference volts, and charge is coulombs. You may have seen the equation written E equals V times Q. The second equation is potential difference equals current times resistance, so V equals I times R, and this is linked to Ohm's law. So PD is measured in volts, current amperes or amps, and ohms or omega for resistance. So then V equals IR, or volts is directly proportional to current as long as temperature remains the same, and that's Ohm's law, and we'll see more on that when we look at the graph shortly. Resistance, which we've mentioned just here, is often symbolised using a resistor symbol. What we really mean though is that electrons are being pushed by the potential difference through a wire, and inside the wire we have lots of atoms that are vibrating backwards and forwards, and it's stopping the electrons from passing. So as soon as we have a charge, or in this case an electron trying to move, we have a current, and that current is trying to be slowed down by these vibrating atoms inside the wire. The more they vibrate, the harder it is for the electrons to flow, So that means the current will be less because the resistance has increased. So just like when you move normally, you have friction trying to slow you down. In this case, with electricity, we call it resistance acting in the opposite direction to what you're trying to do. So for a resistor, this is an ohmic conductor because you have a straight line through the origin. I and V are directly proportional to each other. And the reason they're directly proportional is because the temperature doesn't change, so the resistance in the wire doesn't change. The hotter something is, the higher the resistance because the atoms will vibrate more. So I said earlier, V is directly proportional to I, and that's the symbol that we would use. So I've now added on a blue line just here. And when the gradient is less steep, so shallower, that's when the resistance increases. So the black line has a lower resistance and the blue line has a slightly higher resistance. Both these lines are still ohmic because they're a straight line through the origin. They just have a different value for the resistance. Now let's take a look at some non-ohmic conductors and their graphs. So there's three more graphs to look at. The first one, the filament lamp, second one, the diode, and the third one is the same shape, but you can use it for a thermistor and an LDR. So a filament lamp looks a bit like an S. So we'll just focus on the top right-hand side for the moment. And what that tells us is it's non-ohmic because it's not a straight line, even though it does go through the origin. As you know, when you touch a bulb or a filament lamp, it gets hot, the temperature will change. And consequently, as it gets hotter, the resistance increases. So at low voltages, when it's cooler, then the resistance is lower. And as the potential difference increases, the resistance increases. And that stops the current from increasing by quite as much. The reason I've drawn this part of the graph here is because the bulb can be put any way round in the circuit. It doesn't matter which direction you have the current flowing through it. However, for the next one, it really does matter. So a diode will only work in one direction in the circuit. If you put it the wrong way round, the current stays at zero. There won't be any electricity flowing through the diode because the resistance is infinitely high. However, if you have it the right way round, then what happens is above about 0.6, 0.7 volts, the resistance suddenly tends towards zero. It's a really low resistance, and that allows the current to increase massively for only a small increase in potential difference. So the resistance is high on the left-hand side, and it's really low on the right-hand side. Let's look at a thermistor next. So that's the resistor that changes with temperature. As it gets hotter, the resistance decreases. So something that's really hot will have a low resistance, so that will allow the current to flow really easily. However, when it's cold, that's down here, that's got a really high resistance, so that stops the current from flowing quite as easily. And a thermistor looks something like this. So it's a resistor with like a hockey stick through the middle. Now an LDR, or a light dependent resistor, looks like this, again with a resistor, and it's light dependent, so the arrows go in. Now the shape of the graph hasn't changed. The only thing I've changed is this word here, and I've changed it to light rather than temperature, because the brighter it is, the lower the resistance. And if it's really dim, it's a really high resistance. So the shape of the graph is the same, it's just this on the x-axis that changes. So when they're put together, just change what's on the x-axis, just depending on what symbol you've got. Now on to series circuits. So a series circuit just means the current is the same through each component. Everywhere in one loop, the current will be the same. So let's look at this example. We have a cell here, and the current's going to flow this way around the circuit. We've got two bulbs just here, but the current, no matter where you put an ammeter, will be the same. And I've signified that by using lots of green dots. However, the total potential difference coming from the cell adds up to what it is across both of our components just here. So for example, if we have a 1.5 volt cell, the total voltage that adds up across our two bulbs will also equal 1.5. So assuming that they're both equal, there'll be 0.75 volts across this one and 0.75 volts across this one, because if you add them up, it comes to what you started with at 1.5. And then the total resistance equals the sum of the resistance of each component. So in other words, when they're in series, if you know the resistance of the first one, you know the resistance of the second one. To find the total resistance, you just add them both together. So the thing to also remember, when they're in series, so in the same loop, the resistance will always increase, and that's very different for the next thing we're looking at, which is parallel circuits. A parallel circuit is different from a series circuit. It's when you have more than one loop. So a series circuit just has one way round to go, whereas a parallel circuit, there's more than one way round for the electrons to flow. The rule with parallel circuits is the total current through the whole circuit is equal to the sum of the currents through the separate branches. So let's take a look at another example. So again, we've got a series circuit to start with, but then it turns into a parallel circuit because there's more than one way round for the electrons to flow. So we'd say A1 equals A2 plus A3. What we start with splits into two separate things, and if we put A1 just here again, they would join back together. think of it as cars. If you've got 10 cars to start with, 5 cars might take that road, 5 cars might take this road, and they'd meet just here at this junction, so we'd then have 10 cars going back to our cell. It's worth noting, however, you only get a 50-50 split if the resistances of our components are the same. If the resistance of this bulb was higher than this one, if this was higher, then that would mean the current going around this way would be lower, because it would be harder for the current to get through. More of the current would go through this way. But either way, what you start with is what you end with. When talking about resistance in parallel circuits, we don't need to know an equation like we did with series. All we need to know is that the total resistance is always going to get smaller. By providing more routes for the current to choose to flow through, that means the resistance goes down because it's easier for the current to get through. For potential difference in parallel, it's the same. So if this was 1.5 volts here, this bulb would receive 1.5 volts, and this bulb would receive 1.5 volts. In other words, these bulbs here would be brighter than this one. These were only 0.75 when we mentioned them. Because they're in series, the voltage gets shared. In this case, the bulb will be getting double the potential difference because the cell is having to work twice as hard. So it would get flat in half the time. Using different numbers, let's say 12 volts here, that means that would get 12 volts, and that would get 12 volts. If we added in a second bulb where A3 is, that was the same as this one would still get 12 volts, but these two, the voltage would share, so that would get 6, and that would get 6. So these would be dimmer than that one. We've now reached the end of the video. As ever, if you have any questions, please get back to me. I hope you've enjoyed watching, and don't forget to press the subscribe button. Thank you.